So first things first, apologies from Bob Stanton, our chairman. He normally runs the Zoom side of this. He has family commitments today, so he can't attend. So unfortunately for everybody else, it's me running it. So this may not go quite as smoothly as it normally does, but I'll ask you to bear with me, please. So off we go. So standard format for the day, quick welcome from me for about 5 minutes, and then we'll hand over to Dr. Ian Coxhill to talk about LEROS 4, which I'm very much looking forward to. And then at the end of Ian's talk, we'll move on to questions. Our November talks, we always try to have a propulsion-based talk. And this is in memory of John Harlow, who was a former president of the BIS and founder member of this branch, along with Dr. Peter Penny and myself. We were all propulsion types from Westcott, and sadly both Peter and John have passed away, so we tried to do a November propulsion talk. John and Pete, much missed. So do bear in mind that the branch is a volunteer thing, and if you'd like to help out or be put on the contact list if you aren't already, just send an email to the West Mid Sec, the quick slide showing the advantages of joining the BIS, all the things that the benefits, things we get up to. So please do join the BIS. The society needs you. And finally, there are the magazine editors are always looking for articles. So journal, the long hair articles, Space Chronicle, history articles, Spaceflight, the sort of current populist magazine, and Odyssey, the science fiction type. And then if anybody wants to submit website articles, you're very welcome. So contact HQ or the editors. What I should mention is that every year, as part of Reinventing Space, the BIS run a program of awards called the Arthurs, the Arthur Clarke Awards. And this year, West Midlands nominated the Race to Space team. And we're very pleased to say that they won the category for Space Achievement Industry and Project Team. So anybody not familiar with the Race to Space, do by all means go on to our June talk and have a look at the film of our June talk, which was all about Race to Space. It's an excellent program, really worth supporting and following. And with that, I'm going to pass on to Ian for his talk, and I need to stop sharing if I can work out how to do that.
Well, thank you very much for the introduction. Yeah, this talk today is all about the LEROS 4, and really it's the history of how we landed on the moon. So the guys at Westcott are very proud about this. So I wanted to capture the whole sequence from where it all started to literally the moments where we touched down on the moon using the LEROS 4 main descent engine. I'll explain about how that happened and how it came about, but I'm going to start first with a bit of background history. So Nammo UK, as we're known at the moment, is a manufacturer of liquid rocket engines, and we're based at the Westcott site in Buckinghamshire. And we really have direct lineage all the way back to 1945, when we're under MOD ownership at that point. Now, over the years, we have migrated into kind of civilian ownership and Royal Ordnance, British Aerospace,
Recording
ARC,
in progress.
AMPAC, Moog, Nammo. They're all names, but essentially it all refers back to the same core competencies and associated facilities that we know and love here at Westcott. And also I'm going to refer to just the team as the Westcott team rather than by the actual names, because it gets confusing when we start switching around. So I'll refer to the Westcott team as the guys and girls that do the rocket engine development, which is now under Nammo ownership. Okay, so moving on. So the background is that during the 1980s and 1990s, there was a real push for civilian space to basically make satellites, telecommunication satellites, which would then move the era of, say, Sky TV and that kind of thing into the mainstream. And there was a need for rocket engines to move those satellites around, to put them to the final orbit. Now, Westcott at the time was essentially a kind of like post-military organization that was looking for new ways of basically getting into the civil arena. And the requirement for high-performance, hypergolic liquid rocket engines of around about 500 Newton thrust, or approximately 50 kilograms, was coming to the fore. And Westcott was well placed to capture that market, and indeed they did, by developing the series of LEROS, Liquid Engine Royal Ordnance Space, is what it stands for, rocket engines, which went on to become a staple commodity on board a lot of telecom platforms in the era. Just to give you an idea what I'm talking about in terms of size and dimensions, on the right-hand side here, we have got a LEROS 1C engine, which is one of our top-selling units. It weighs around about 4 kilograms. It produces around about 50 kilograms of thrust, as I said, and there is a Coke can there to give you an idea of scale. Okay, so during the 1990s, there was a range of LEROS engines developed, LEROS 1B, LEROS 1C, and also the LEROS 2B. And you'll notice here that the LEROS 1 series burn hydrazine as their fuel, and the LEROS 2 series burn monomethyl hydrazine. That's primarily dictated by the end customer. Some customers want to use hydrazine, some customers want to use monomethyl hydrazine. They have their benefits and disadvantages, each combination, but nonetheless, I won't get into that today. But they all burn the oxidizer MON3, and that's mixed oxides of nitrogen. Basically, dinitrogen tetroxide with a small amount of nitric oxide mixed in with it. These are all hypergolic engines. They are all bipropellant engines, so they spontaneously ignite on contact between the two propellants, and that makes them extremely reliable. So you don't need an ignition system. And this is one of the principal reasons why the telecom era wanted to use these kind of engines, is because they were reliable, and they basically, if the valves opened, they were guaranteed to work. So what is a typical application? Well, as I said, geostationary satellites is often what these types of engines are used on, and satellite TV is a good example. So things like Sky TV would use this, and the way it works is the satellite would be launched on a launch vehicle, which would drop it off into geostationary transfer orbit, or GTO, and then the onboard propulsion system, the main engine, or the LEROS engine in this case, would then move it into the final orbit, into its circular orbit with an orbital period of 24 hours. But the GEO platform, or the GEO belt, is not just limited to telecom platforms. It's also used for more unusual missions, like, for instance, missile defense. And there is the US, what's called Space-Based Infrared System, or SBIRS, which is a dreadful acronym, but nonetheless one which the Americans insist on using. That we're actually quite proud that we actually supplied the LEROS 1C into that platform. Now, each of those satellites cost about $1 billion, yet the Americans trust the LEROS 1C made in the UK to put that satellite into the correct orbit. And I think that's certainly something in the UK we can be proud of. Now, on this artistic render you can see here, you can see that they've actually incorporated our LEROS 1C engine onto the very bottom of it. So it's a fairly accurate picture of the SBIRS spacecraft. Now I'm going to show you a video clip, and hopefully it works. It should play, hopefully. Let's manually play it. There you go. So this is the top end of an Atlas V releasing the SBIRS spacecraft. And if I just pause it there, you can see as the spacecraft separates from the launch vehicle, you can see the LEROS 1C main engine on the underside of the spacecraft just disappearing into view, and then obviously disappearing into space as it's been released into this geostationary transfer orbit. So the spacecraft will stay in that orbit for a few days, and then it will fire the LEROS 1C for a number of times, potentially up to several hours, to put it into its final orbit. Okay, so geostationary spacecraft is all very well and good, but what really kind of floats my boat in particular is the interplanetary missions. And Westcott has been involved in a whole series of interplanetary missions over the years, which is quite exciting. Some of them include going to Mercury, for instance, Mercury Messenger spacecraft. That was the first time that an artificial satellite, a man-made satellite, entered Mercury orbit. And it was a LEROS 1B engine which actually did the braking maneuver to drop the spacecraft into that orbit. So that was definitely quite a proud achievement. There are other things which we're very pleased about. For instance, the first landing of another asteroid on the asteroid Eros was actually performed. They used a LEROS 1 engine to slow down enough to be able to be captured by that asteroid. So that was another first. And we've got a number of Mars missions as well: Mars Odyssey, Mars Global Surveyor, and also Mars Climate Observer. So there's a trilogy of missions to Mars in the 1990s. Now, unfortunately, the Mars Climate Observer didn't quite end as planned. And if those of you who remember, there was a bit of a units conversion issue between pounds force and newtons. I've got to say that wasn't performed by us. It was performed by other people in the food chain. But unfortunately, that spacecraft entered the Martian atmosphere and actually burnt up. But nonetheless, the LEROS 1B on board performed flawlessly. So, okay, so bringing it more up to date, we've got the Juno spacecraft, which was launched in 2011 and arrived in Jupiter in 2016. That used a LEROS 1B to do the final braking maneuver to put the spacecraft into the Jupiter orbit. And bringing it right up to date, we've got Lucy, the NASA Lucy mission, which was launched in 2021. And that's currently en route to, it's not actually going to Jupiter, it's actually going out to the orbit of Jupiter to visit what's called the Trojans. These are a series of asteroids which are in the Jupiter vicinity, shall we say, in the same orbit as Jupiter around the Sun. And they're the remnants of what scientists believe was the start of the solar system. So whilst most of those asteroids accreted to form the planets, they're also left over, let's call it space junk, space rubble, that by observing that and making measurements, we can tell more about the early days of the solar system. So the first interaction is going to occur in 2027 when Lucy finally reaches the first of those Trojans. Okay, so let's now talk about LEROS 4. So that's a bit of a background behind the LEROS engines. What about LEROS 4? Well, in 2009, we were invited by ESA to submit a proposal for a new type of engine, a new engine which is going to produce about 1,100 newtons of force, so around about 110 kilograms of force. And that's around about 2.5 times the thrust of what we call a standard LEROS apogee engine. And its intention was primarily for interplanetary use. Basically, for interplanetary work, the higher the thrust, the better. You can do more, you can get more payload to a particular point by using a higher thrust engine. So that was ESA's motivation for developing this work. So Westcott submitted a proposal, and fortunately we were awarded the contract, which started with an initial theoretical study phase, as most of these projects do, and that was really to understand what kind of materials do we want to use, what kind of structural analysis and thermal analysis would lead to certain design factors, and what development plan you're going to use, and also what test facilities you're going to use. So we completed that work successfully, and we're making progress, and that then followed on with the actual basically hot fire testing components. That's where we actually did sort of making some basic engines and starting to hot fire test to prove that it actually worked. So a LEROS 4 rocket engine is comprised of basically 4 components. You have the valves, which you see on the right hand side here. You have a zone, which is what's called the head end or injector assembly. And then we have the combustion chamber, and then we have the expansion cone. Now, breaking it up into those 4 components, which is the same basic 4 components as the LEROS 1 and LEROS 2 engines use. Basically, we're leveraging the experience that we had in the 1990s. By breaking it into those 4 components, we could then parallel up the work scheme so that we could have different teams working on the different zones of the engine in parallel in order to meet the schedules that were posed. Now, the biggest challenge on an engine like this, and it's always the biggest challenge for rocket engine development, is the injector and the combustion chamber design. So that's the area which we tackled first, and that was the reason for ESA issuing us the invitation to tender to start with, was really to concentrate on the injector technology and the combustion chamber technology. So with that in mind, we started the development of this curious looking device. So this was really the injector and combustion chamber test article. And you can recognize that it does look like a rocket engine because you've got valves at one end, you've got a flange here which contains the injector, and you've got a rather stubby combustion chamber. Now, it's a stubby combustion chamber because it's got a very small expansion ratio. So in other words, very small expansion cone on this device. It doesn't have the big expansion cone like you've seen on the previous pictures because it's not designed to be tested in space. It's not designed to be tested in vacuum. It's to be designed to be tested at sea level. Now, for the initial combustion studies, that's fine. You can do that. And that's a good way of cheaply optimizing, or relatively cheaply, should I say, optimizing the performance of the injector. And to give you scale, that diameter across there is about 56 millimeters, so just over 2 inches. So relatively small compared to the final engine.